So thank you everyone for coming for my last or my second to last lecture. And this lecture will be dedicated to giving you a proof of resolution singularities for curves. And this will be done through normalization. So this is how normalization of curves. So this is actually a very nice, very minimalistic proof of resolution of singularities of curves. However, it is far from being the first proof of this. It was actually given to us by Zariski in 1939. So it's quite recent. 17 years would be only 100 years old. The reason it was a little bit complicated was because we needed to invent the concept of normalization. So I'll expose today the very basics of this process. But first of all, let's do a little bit of I'll try to do an example and also recall a little bit of things in the first time. Okay? So let's get an example first. And let's take our node, right? So the node, as always, its equation is this. So remember, you always have this lovely loop. Well, first term, this is the point. Okay. And if you remember the very first lecture I did, I took a line through it and called this its slope. So it was we have a point say y and x, and you have the point where the slope would be x and y. So this is the picture I want to have in mind. So we obviously have a singularity here, right? We already know that. And we found a parametrization, okay? Given by t. So we take, so we'll just call this, let's say, how did I mention it? Yeah, okay. So this will be my polynomial, this will be my curve, and it will be inside the plane. Right? Whatever field you want. So I'll take, so how do I parameterize thanks to t? I take, well, any value t, and I try to make it equal to y of x. So I replace, I try to find equations for x and y according to t in the equation. So if I have y is equal to x squared 1 plus x, I divide by x whenever x is different from 0. So I find y over x squared is equal to 1 plus x. So t squared is equal to 1 plus x. So x is simply t squared minus 1. And to obtain y, I just multiply by t. Okay. So, yeah. So this is a birational morphism. Okay. Birational morphism. And we have, so did I give it a name? Yeah, F. And outside the singularity, it is they are only 1 to 1, but we have 2 points at 0, above 0, which are t equals 0 and 1. Okay. So this was the geometric picture we had, and as you can remember, at the very first lecture, we saw this morphism. So it's kind of a callback to that time. But now we have a lot more algebraic tools, so let's try to see what happens at the level of algebra in this section. So when we have a morphism, we know that we have, how do you call this? A morphism of the coordinate rings of these algebraic varieties. So, okay. So we know that we have, well, okay, maybe it's going a little bit too fast. But just plainly, we have a morphism for the coordinate rings. So, and we know that this is a birational morphism. What does that mean? That means that these two rings have the same quotient, field diffraction quotient, right? So they are all together inside K of C, which is isomorphic to K of A. So what is this? If we try to look inside of it, as you can remember, this is just, we just quotient the two variable polynomials by the equation. This here is just K of T, okay? So here we have an inclusion where we take the variable x bar to square minus 1, and here we take do the other side t times t square minus 1, like that. Okay, and obviously these are equal to rational functions, like that. Okay, and why is this interesting for us? Well, at least what is the point I'm trying to get here? My idea was to illustrate that this is our first example of a resolution of singularities. It was at least when we were on our first example. Of singularities. Now, the reason I insisted particularly on the last section on curves was because for curves we had a very interesting characterization of smooth curves, which was by a very simple, rather simpler algebraic condition, was to say that it was a normal variety. So recall last lecture, so lecture 7, if I'm not mistaken, a curve is smooth if it is normal, right? So that would mean that covered by a fine opens with a U integrally closed. Okay. I'll redefine what closed means, and I'll recall these definitions in this manner. And here we have an example of this, because this here ring, it is normal, okay, so because it is an UFD. Okay, so naturally it's the variety it comes from is smooth, it's pretty obvious. But we have an extension of the coordinate ring of our curve here, right? I'll deliberately call these inclusions of rings extensions of rings. And this extension here is called integral, meaning that every element here satisfies a polynomial equations, a monic polynomial equation with coefficients in here. And up And this extension of rings here is integral. And this is what I wanted to come to is to say that this will translate once we establish the basics about normalization. This means that this is the normalization of C. And this is what we are going to try and find out. The idea is to try to take our original singular variety and try to find another one, okay, which is smooth, okay, and that parameterizes the curve C, meaning that it is birational, so outside the finite number of points it will be an isomorphism. And for the singular points, its fibers will be finite sets of points. Okay? And the tool we will use for that is going to be the normalization. Okay. So this is just a little bit of a warm-up to see how we are going to work with this. Okay. So unfortunately I'll have to erase at least half this. And now, I need to establish the vocabulary. So this is the beginning of a more technical part. Okay. So, okay. So, I'm going, just for clarity's sake, I'm going also to recall what integral close means, all these terms will be fine for now. Okay. Let's be a morphism of rings. We also talk about extension of rings. It is an inclusion, and right. So this is very close to how we write about field extensions. A lot of this terminology is actually a generalization of the term of algebraic extensions to rings. Okay. So, we say that is integral, is unintegral extension if every element of V satisfies the Monte coefficients, coefficients in A. So for every B, there exists P of X. So this is a Monte equation. Okay, the important part is that it doesn't have, there is no coefficient here. It's such that P of B is equal to 0. Okay. So this is integral. Now a ring, a domain. And now we got the hypothesis that we have domain. A domain is integral. Let's see, integral closed. If any A in the fraction field, if A is integral over A, then A is actually in A. So there is no element beyond A that is integral over itself. So in order to obtain these integrally closed rings, what we do is take a domain A, then its integral closure is the set of elements in the vacuum field that are integral over A. Yeah. So another way to formulate condition B is to say that it is equal to its integral closure. Like that. Okay. Well, there is an even more general, let's say, notion of integral closure inside of an extension of the base field, but we won't deal with that here. Okay. Now this is the algebraic part. There is also A, B, C. Let's see D. Let's a morphism between affine varieties. Okay, so morphism between affine varieties is will be called finite. If, well, the real extension is integral. There. So, and okay, the global definition is between arbitrary varieties is finite if it is covered. Okay, so Y so if I can find for any point in Y, I can find a neighborhood. Okay, so this is open. Okay, set affine. You can find an affine neighborhood at this point, such that, okay, so this is a particularly special condition, such that its inverse image is also affine, and the induced map is finite. So in order to define the general notion of finite morphism, I need to go back to affine covers. But with this extra condition here, which is a very special one. So if you remember, I did a little bit of a drawing last time, and this is actually illustrative of the property, of some basic properties of finite morphisms, hence justifying its name. It's that it's basically we take a variety X above Y, and we twist it around so that, and then we project it. So this is kind of the image we have about this. Think of finite morphisms as covering spaces, topology. And this is also kind of the motivation. Because this strategy is actually this whole process of normalization, and the whole intuition behind it was to come back to Riemann's topological proof. Riemann, the resolution of curves, has had a lot of proofs before Zariski, and the first one dating back to Newton. And a very abstract and very cherished proof was that given by Remap with purely analytic and topological tools. And normalization, it was an attempt to actually encode algebraically, purely algebraically, I mean, his constructions. Okay. So these are the tools we mostly have, and of course the example I started with is the prototypical example for these maps. Okay, so the map A1 to C was a finite map. Okay. If we take the example I'm going to mention. Now, of course, this is okay. So this is for a radial expression for D instead of E. E is to generalize this for projective varieties. Now remember, projective curves are described in projective spaces, but it is covered by fine pieces, fine charts. Okay. Okay, so now I'm going to just give you a couple of properties of these types of maps. The basic, let's say, algebraic tools, our toolkit for this. Okay. Which one should be? Okay. So the first very basic property is that if I take V, a finitely generated A algebra, then the extension V over A is integral if and only if B is a finitely generated A module. Now remember that these two things are very different. And going from an algebra to a module is a rather difficult process. It's really nothing to do with each other. So this is mostly we take the generators, and since the generator will satisfy the polynomial equations, you will see that basically what's the main idea behind this is to show that these are integral extensions. So this is mostly how these this works. This is mostly the picture we want to have in mind. Okay, so being integral is a transitive condition. This is actually a pretty interesting exercise you can do. Transitive So if I have C over B and B over A integral, then C over A is also integral. That this is one. Okay, but what about the maps? Do we have some properties for them? Well, if I have an affine, it turns out that we only need the affine case of this. An affine finite morphism is subjective. So you'll be a bit surprised, how does that actually work? Well, this actually is something that comes from commutative algebra, or something that you have seen in algebraic number theory, coming from the line over, let's see, was it lemma theorem in the Cohen-Seidenberg theorems. So what does this mean? It means that if I have, let's see, if I have a ring extension A, and if I have a maximal ideal here below, let's call it M, then there will exist a maximal ideal over it, like this. Exists such that like this. Okay. And if you remember, maximal ideas correspond to points. Maximal ideas of the coordinate ring correspond to points. So if I have, let's say, this is B, okay, so if I have this is ax and this is ay, if I take a point in y which corresponds to the maximum idea update, I lift it to a maximum idea of the ring above, which is the coordinate ring of x, so it is a point of x that corresponds like this. Okay. Let's see. Okay. So, okay. So why am I bombarding you with all these notions? Well, the idea is to come to the normalization. And a normalization of a variety x is, let's say, how can I say, is a variety x bar that is normal and a morphism, a regular morphism x bar to x, so sometimes we call it nu, the Greek dicta for n as a normalization. That is birational and finite. Okay. So we have x here, okay, and we want to find a normalization above. So something will be singular here, or maybe something a little bit stranger here, and the normalization will be something that was supposed to be a resolution of these things. So let's see. This will be like that. Okay. Now, birational, that just means that nu induces an isomorphism between the function fields. The two. Okay. So this is our objective here, and we know that if we have, so this is smaller than smooth in general, but we know that it is equivalent to being smooth for curves. So our main objective for the remaining part of the lecture will be to construct the normalization of curves. So, and we'll see how these concepts and these properties come into play in its most basic construction. So, this will come in several steps. It is a pretty involved process. So the first step is the affine case. So my goal will be to build the normalization of objective to be the final goal of objective curves. So the step one will be to consider the affine case. Okay. So if x is an affine variety, so this works for any affine variety. And I'll focus on curves beyond step number 2. Okay. Then x bar and nu exists. So this is how I wrote its normalization, and is affine, meaning that this x bar is affine, of course. Okay. So how do we do that? Well, it all involves, if it is all affine, it all should be happening at the level of coordinate rings, right? So I have a of x, its coordinate ring. I have k of x, its function field. So I know that a of x well, there's an inclusion between the two, but I know that A of x is potentially not normal. Hence why it would not, if it's not smooth, it would be not normal. So the easiest way to think about finding something which is smooth is to take its integral closure. Okay? So I talk about A, I write A to be the integral closure of A of x, like this. So normally A of x is included inside, and all these elements are just elements of the fraction field. Okay. So naturally I have, so first of all we have that since A is between a ring and its quotient field, naturally they'll have the same quotient field, right? Right, this is the x. Okay. The second point is that this inclusion here we want it to be something coming from a variety, right? We want it to come from an affine variety. Affine variety x bar such that A of x bar is equal to A. Then it will be equal to that. But if you remember what the correspondence we established when we were talking about the Nurstone maths, we need, so we need the ring A to be a finitely generated K algebra. And unfortunately, I'll have to use a black box here because the theorem itself will take the rest of my lecture, to be honest, if I want to establish it fully. So, what I'm going to use here is a very celebrated result of Amy Noether, among most of the results, to be honest. But this is called Noether's theorem for affine domains. Okay, domains, meaning that that will establish actually that the ring A, this is A, in the exact conditions we are given, A is a finite, let's see, finite AX algebra. Hence, so the direct corollary is that it is indeed a finite algebra. Hence, finite algebra. Like that. So this is a pretty involved result to get to. Interestingly enough, it needs to separate between the two characteristics. Either we have characteristic 0, in which case it is relatively easy to establish, but there's also the positive characteristic case, the positive characteristic of the field K here, in which case this process needs a bit of work, a bit of extra work. Okay, so this gives us, so we know that this x bar exists by virtue of just finding generators of A. This will give us the x bar.
I think you need that A is a finite AX module. No?
Is it finite? Oh, no, yeah. Module, yeah. It's interesting because I was exactly hesitating between is it algebra or module, and I was thinking module, but said and wrote, sorry. Yeah, it's a finite module, which is a stronger result than what we need.
Yeah.
But unfortunately, I don't really no proofs that are simple then. Going
Yeah, no, there is no simple proof.
There's no simple proof for this, unfortunately. So x bar exists and is birational to x. The morphism deduced from, so we have the inclusion between the two here, is finite by construction. I mean, this is integral because we took every element here to be the whole set of integral elements here. It's finite by construction. Okay. So first step of the normalization of curves is, okay, we have the affine case is mostly done. Okay. Now, in order to establish the normalization of general, we'll start first by quasi-projective curves, then we'll establish the one for projective curves. Now, the idea is that, unfortunately, we need to work a little bit more, let's say, functorially. That's the way, let's say. Is that in order to work with affine charts and have an efficient way of managing the different covers of this, we need a little bit of work, of functorial work. So now that we have a little bit of a grasp of how normalization works, so at least for affine varieties, this works. In actuality, it works for any variety, even for something more general like schemes. But unfortunately, that will be too much work to do here. Okay, so the term I want to work with is the universal property. Of normalizations. So I'll just abbreviate it with UP, universal property. Okay, and this comes in two parts. Okay, so if I take for every y to x morphism between two, let's say. If I take a morphism of affine varieties that is finite and birational, okay? Well, I know that we have a normalization. Okay? Then I can establish the unique existence of a morphism from the normalization to y. So I can lift the normalization morphism to y, like this. Okay. And this basically establishes this, that this is unique. So it exists unique H that makes this morphism work. So this is lift to a finite, let's say finite extension of x. Okay, this is the first part. The second part is actually something that is a dual version of this one. So if I take yx again, a morphism of affine varieties that is only dominant and y is normal, So if I have something normal that it's coming in on x in a dominant way, so dominant, if we don't remember what it means that j of y is dense in x. Okay? Then this actually will factor through x. So we actually have the other way around. Okay, let's write it k because we have an h here and k. So any normal morphism that comes that dominates x actually factors through its normalization. So a normal variety that dominates x factors through x bar. So sometimes you see this as the only definition of the universal property of normalizations. However, I also include this part here because it is equally useful. Okay. So the proof of these is actually quite easy. So I'll just briefly sketch them.
Well, in the second case, k is right inverse of h.
No.
Or left side of the chromoid one, because we can apply this to.
Oh well, if you have y which is this morphism y and j that satisfies the intersection of these two conditions. So if y is normal and if it is finite by rational, but that's the normalization in some sense. And this is actually the corollary, right? The corollary means that if I have two normalizations, then there will be isomorphic, and this h and k will be the inverse of each other, right? So this is a kind of an immediate corollary, is that the normalization is unique to unique isomorphism. So if I have two normalizations here, yeah. So this is exactly what you're describing, right? Is that if I have two normalizations here, into one, so
But at some point in this lecture, we are talking only about curves, so.
for now we are so this the first step. I'm talking in general for general varieties. From step 2 and beyond, only curves. But they are still for general varieties. And there exists a unique isomorphisms between the two.
Yeah, this theorem is valid for all dimensions.
Yeah. Well, this is just an application of that. So a sketch proof of UP goes basically as follows. We just need to take the coordinate rings, actually. So we have a of y on one side, a of x on the other side. So we have the morphisms that it is given between the coordinate rings functorially from G. And let's say, okay. And of course, new x bar here, star here. Okay. Now, we also know that this AY is included in K of, K of Y, it's function field. But since it is by rational, this means that this is isomorphic to K of X. Right? And all these I included in f(x), like this. And where did I put this? Okay. Now a of y is integral, so this is integral, and a of x bar is the integral closure of a of x, right? So anything that is integral over a of x and included in the function field is normally included in the integral closure. So there's actually an inclusion here, like this. So, and this will give you the h, right? Gives unique h. Okay. There, like that. Okay. Is it clear like that? I mostly said it up already, but I should. Okay. And the second part is mostly the same type of reasoning. So the point number 2 is mostly the same thing. Well, mostly the same thing. So we still have a of y that is included in k of y, but now k of y is not equal to k of x. Since it only dominates, that means that it contains k of x. Right? Like that. Okay. And of course, we know that k of x actually contains a of x bar, which itself is the integral closure of a of x. And of course, we have the box in here. It also happens to be an inclusion because it is it composes to an injection here. Okay, but let's see what we need. What we need is a morphism that goes from y to x bar. What does that mean? That means that on the coordinate plane we need a morphism from here to here. Right? So the solution would be to find, to see if this inclusion, so if seeing this string here as a subring of the function field of y lifts to a of y. But remember, this is integrally closed. Okay? Because y is normal. This is integrally closed. Okay. So if I take an element here, then u, an element of a of x bar, u is integral over a of x. This is just because this is the integral closure. Okay. This means that u is, if I consider it as an element of k of y, not just k of x, but k of y, then if it's integral over a of x, it is also integral over a of y. A monic polynomial in coefficients here is also a monic polynomial in coefficients here. Like that, right? But if, since a of y is integrally closed, so this inclusion, so a of x not only arrives in k of y, but actually arrives in a of y. And this red inclusion will give us our unique k, like that. Okay. Okay. So this is just a version what we will go. Okay, so this is a bit often called this abstract nonsense, because we have this very general situation, and just by unwinding the properties we arrive at these morphisms that are relatively abstract. Okay. So for now we have these tensorial properties of the normalization. Okay. So step 2, and now we are going to restrict to curves. Quasi-projective curves. Normalization. Quasi-projective curves. So I would say that this is mostly the meat of all these quadratic properties. So very well. So this will take, let's see, 1, 2, 3, 12, 8 steps mostly. But each one is meant to be something simple to digest, of course. First of all, we want to cover a quasi-projective curve. X, they call it X, yeah. Pn, like that, by an open affine cover. Open affine cover, U, I, affine open inside X. Okay? So how do you do that? Well, remember that if we have Xi was an affine open. Okay, so this was the points x0, xn, homogeneous coordinates, such that xi is different from 0, right? And this was isomorphic to AFN. Okay. Yeah.
What is this DP?
DP is this. This is the standard open.
Is it just DXI or?
Or I just put the P here just to have projective inside of it, because there's also the standard open for affine. But yeah, okay, it's.
No, it's fine. Yeah.
So this is an affine variety inside of Pn, and if you remember the dehomogenization of varieties, we know that also X intersect with I. This will be an affine open index. So okay, very well. With but we have all this projective space. We kind of need to a little bit forget about the projective space. Okay. Okay, so let's forget about the projective space. We have an affine cover of our curve. Okay, X inside of the projective space. Okay, and we call these open affine subsets UI. This is step 1. Okay, what do we do with these affine opens? Well, natural step would be to normalize each affine piece, right? Normalize each affine piece. Okay, so maybe we have an affine cover UI over here. Maybe we have an affine cover UJ over here. So we normalize this one, okay? We will call it U bar J, as you can imagine. There's mu J, its morphism. And we have another one here. So this is this segment sides. UI bar, UI here, and the whole point of this theorem is to say, okay, how can I build? So these are local charts, local normalizations. How do I build a big one? So for instance, what happens here on the overlap? Can we glue them together back? Okay, so this will be the work we will try to do in the next sections. So let's see. Okay, normalize the teacher find opens. So the UIs, and we also want to project it. Okay, we want to work in the projected space, so we will also take the projected closure. So this is the homogenization of varieties. We dehomogenized here, and here we again come back to projective space and consider their projective closure. Okay, so we have UI. This is the normalization. This is affine case. Okay, this is step one. And we also want, so we know that this is inside some affine space, which can be embedded in a projective space PNMI, and we consider its projective closure VI. So this is projective closure here. Okay. So what I really like about this proof is that it really compounds all of the stuff we talked about until now. So it's pretty nicely wrapping up. Okay. So now we are going to try and build. Actually, the third step is actually going to build us the candidate that we want for our normalization. So, building our candidate. So we take all these maps here, and let's see. The remarkable thing we have until now is that everything up till now is birational. Okay? Every map we have is birational. So we can actually connect every type of set or variety we have until now by birational maps. So I'll illustrate how only the ones we are interested in. Okay, so we have X, we have an affine cover UI here, okay, and we normalized it here, like this. We can also do the same, so here it is, if you remember, it is birational. Okay, it is birational finite. Here we have a non-empty open subset of X. But remember that X was considered irreducible, and any non-empty open in an irreducible variety is dense. Right? So this is a dense open, hence it is birational. Okay. Dense open in X irreducible. Okay. But you can do that the same with with another one. So let's, for instance, consider another index J. So you have the affine chart, but also I'll directly go to the normalization, UJ, and I can consider its projective closure. Okay, so this is also set. So, if you remember, this here is actually a closure, a topological closure for the Zariski topology. So this is also dense, and we can also, if you remember, it was also the U bar here is actually an open subset, so this is dense open, so it is birational. Okay. So this is also birational by the composition of birational here. So I can consider a birational map just by going for this here path, let's say path of different birational maps. Okay. So, but there is an extra ingredient in our work. This UI. Remember that this here. Okay, let's take the green one. So this here is a normal curve, hence it is smooth. And if I'm not mistaken, the very last result we established last week, let me see, verify this quickly, was the, okay, so it was not the very last, okay, far from it. But this means that phi I, we have morphism phi ij, which is birational to Vj, and this is smooth, regular. So that means that the indeterminacy locus is going to be empty. This is a projective variety, right? So this is a projective variety. Hence, phi ij is regular. So what we started with a birational map coming from all these coincidences actually are perfectly determined. Okay.
Okay, can you repeat this last line of argument?
Of argument? This is okay. So this is the result we established last time about rational morphisms coming from smooth curves. Okay, so lecture 7. If x y is a birational, no, not even birational, but rational morphism with y projective and x smooth, then the indeterminacy locus of f is closed and codimension equilibrium. Like that.
Absolutely. What you meant to say here is that the map from U I bar to Vj does not have an indeterminacy locus.
Yeah.
That it is regular. It's a regular map. Okay.
Yeah, it is a regular map. So it's defined everywhere on UI. Like that. Okay. So this was really a bit of a surprise map.
Because a priori, this is a map defined on the intersection of UI with Vj.
Exactly. It's supposed to be defined only
Away. Well, on the intersection.
Yeah. Everything here is irreducible, so any two non-anterior will have a non-triple intersection. Okay, so this was a callback through the last lecture. So this is And we define, so we are going to define the, let's say, we compound all the phi j's with I fixed. And we take the product of the vj's. Right? And we just define phi as being the map defined by, okay, phi I1, phi I2, and all that. So it's, well, it's a bit of a, I call it diagram construction, it's not that. And x prime, which will be our candidate, how do we define it? We are going just to take the union of the images of these maps inside of this big guy here, over here. Okay, up, and this. So this is how we build our candidate, and we need, of course, to prove most of our things. But how do we prove this? I mean, what do we need to show in order for this to be the normalization we are looking for? Well, we need to prove several things. So, what do we need to do? Okay, yeah. Well, what do we need to do? Several things. First of all, that it is quasi-projective. Second of all, we need to show that it is irreducible. Then C, we need to show that it is normal. And D, we need to build a finite birational morphism x prime to x. So these are, let's say, the four main steps that we need to show, or at least work with. Okay. Now, this will be the meat of the actual method. Just the rest was more or less just playing around with everything we have learned up till now. Oh. For this, unfortunately, I need to show to you guys how much I love diagrams. So, if you didn't know about it, then today you will suffer for that. Okay, so, first of all, how do we build these things? Well, the step A and B will actually give us a sort of gluing of these maps that we have reached between the normalizations. Okay, so in order to do that, I'll establish a common open subset where I can work with. So this is non-empty. Why is that? It's because all the UIs are non-empty. And remember that we are working in an irreducible variety, so everything, so any intersection of non-empty opens is non-empty.
So is the notation correct?
The UIs are finite.
No, the i's go from 0 to n, no?
Yeah, but I know.
So why would you denote U0?
U0. Okay, yeah, I see what you mean. Okay. Well, call it union. Okay. Let's take that one. So it's a non-empty dense order. Okay. So in fact, most of the things, in order to prove the gluing, what we actually do is prove that the maps will agree on U infinity instead of just the overlaps. Why? Because of the density and the extension principle of identities. We established also a while ago when we were talking about regular functions. Okay. And we will also consider its normalization. So this will have its normalization as well. And it will also be included in all of the normalizations of the UIs. So I'll show it just a little bit right now. Let's see if I need to show it next. Okay. So I will draw here a diagram that I will keep along the way. So to explain a little bit how these things work together. So we have U infinity bar and its normalization here. Right? I'll just give it a name here for the normalization, just mu. Let's even put mu infinity. Okay. It is included in X. Okay. Since it is an open inside of X, like this. Now I have UI also included in X. It also has a normalization, ui, and of course the U infinity is included in all of these UIs, right? That's the intersection. Now, how do I establish a morphism between the two? Well, this is where the universal property comes into play. First of all, I can use the universal property to where am I? Let's see. Okay. So we remember that this is a dominant morphism, so I can actually, well, it's even a birational morphism here. So I can actually lift, I can compose this morphism here like this, then I can actually lift the morphism from U bar infinity to UI to U bar I. Because remember, this is normal, this is a birational morphism, right? And the universal property guarantees me that the second part, if you have the dots on the eyes like this, guarantees that I can lift this morphism up like this, such that everything here commutes. Okay, I can also do it for a second half. Let's see, UK. So I can do the same process over again here. I have UK bar here, and I have also here. And of course this is an inclusion because it's okay.
Maybe it's a good idea to have some intuition why this diagram works. And perhaps the reason is because all these U's are just the original curve minus a finite number of points.
Yeah. Any U something is X minus a finite number of points. Finite number of points. So, for some sense, normalization, what we'll do to it is going to add a number of points just to make it normal. But if I have a smaller open, I'll need to add a smaller number of points. This is why it's technically included inside. Like that. Okay. Now, if you remember, we also mentioned the maps going to Bj. So if I take the normalization of one of the affine charts as a map from here, which is included in its Vj, this, and we remember, if you remember the phi I maps go like this. So this is phi k j. This is phi I j. This. And we also have the product. Over here. So this is just projecting from this product. So this is the G of the product like this. Okay. So I will add extra information for some other steps inside of it, but I want to keep it like this. Now, my objective is to show, at least first of all, that this phi ij and phi kj restrict to the same map on U infinity. But actually this is already proven from the diagram. The whole work has been done by drawing the diagram. Why? Because this is commutative, this is commutative, everything here commutes. So actually, what I know is that if I restrict the phi kj to U infinity, I'll obtain this central map O to Vj, right? So I know now that phi ij and phi kj restrict to the same map over U bar infinity, which is simply the central composite morphism composition in the big diagram. Okay. So if all of them correspond to each other, so we can actually compound them together to obtain the general morphism to W. Let's see if I can have a different color. Okay. So remember. This is phi k and this is phi I. So if all of the components of phi I and phi k correspond on infinity, then they correspond to each other. Okay. So phi I and phi k agree over U infinity bar. Okay. So at least we have one identity. And call this common restriction, this common phi. Okay. So this big morphism that goes through from U infinity to W. Okay, so it goes from infinity to W. So this is the central map. Central spine of the diagram. Okay. And the main interesting part we have done now is that actually every, if you remember, so x prime, no, I'm not going to write it here because I'll need that space. This one's actually better. So remember that x prime was the union of the phi i's ui bar. And actually, we now, thanks to the map phi, we can actually sandwich each of these components between two parts. So obviously, I can include the image of mu infinity inside the image of I. Pretty obvious, because of the inclusions of this space. Now, what is less obvious is why I can actually include these things inside. I include all of them in the Zariski closure. Zariski closure in W. Like this. The reason here is that all these maps, remember that all of these opens are dense in each other, right? So this here inclusion is dense open. So naturally, if I take its closure, then it will normally contain everything it needs to be included. Okay. And as we mentioned over here, well, already, and phi u infinity bar, second bar, deprived of a started finite set of points. Like that. Now, the other element of answer here is that this is actually projective. Why is it projective? Well, each of these pieces, V of J, is included in a certain projective space Pn. So this is closed inclusion, embedding. And if you remember, this here is projective for a symbol, and this here is I don't have any more. Okay, projective. Why is this a product of varieties projective? If you remember, we already looked at a certain map when we are talking about morphisms in general, which was the Segre embedding. The Segre embedding would take two projective spaces, the product of two projective spaces, and it would include it inside of a bigger projective space as a closed embedding. It's projective because of the Segre embedding. Okay. So this also proves, okay, it proves A, but it also proves B in what we are hoping for. Okay. Very well. Now the part we want to establish for C, so okay, we need a bit more. For the noise. So happens that this was so for step C, we need to know that x prime is normal, right? For that, it suffices to show that the morphisms, let's see. So we have u bar 2 phi I u I bar, which is included in x prime. That these morphisms are actually isomorphisms, not the phi tilde. Now, the reason I call them tilde is that phi I is actually a composite morphism, but I mean, I just take its image like this, that the phi I tilde are isomorphisms. And since x prime is covered by normal affine opens, they need to be normal. Hence, the definition works. Okay, but actually we can exhibit the inverse of these maps. Phi I tilde has an obvious inverse. So if I take, so if I decompose phi, so remember that phi, well, even phi tilde if you want, is phi tilde I0, phi tilde I1, and so on. But among them, there's the one that is more important than the others, phi I. Now, and this is the one that is going to give us the answer. And what is this map phi ui I? Well, it just takes us from ui. No, sorry. To let's see, to vi this. But consider if I take x in phi wait, no, sorry, ui, I'm just going to take as the inverse image phi I minus 1 of so the inverse map is this one. Let's see. Very good. So it is normal. And finally, the very last step, hopefully I'll manage to give it here. We need to build the map. Okay. So we consider the composite map. Phi I ui bar, which okay, so we know that it is isomorphic via phi I to I bar. And we know that this also has a morphism that goes to x, which is this composition here. Very well. So let's, so the final nail, let's say, in all these maps is going to be, we'll have phi ui bar, this, which is included in W, and okay, this is just phi tilde. The final map we consider is just one coming from here to here. This is map J I. Here. And we have the same one on the other side. Okay, I won't provide that here. And for now, you think, okay, in order to show, for now we know that this is a regular morphism. Okay. And we can glue them together. Yeah. That we can do. So regular morphisms that can glue. And for that, it suffices to show that their common restriction to phi u bar infinity agree. right? Because why? Then we'll have to go to the class. Now, if Ji and Jk agree over u infinity, then this one being included in phi I vi intersect with phi k bar k. Remember that this is dense, right? By the identity principle, Gi and k will agree on the whole overlap, right? I on phi k k. Okay, so how do you prove that they agree with each other? Well, this is the interesting part, is that you only need, so to show that they agree, you just need the following compositions to agree, actually. If I take the I compose it with phi I tilde, and I restrict it to phi of u infinity. And then I do the same thing for the other one. So why does this suffice? Well, remember that this is an isomorphism, and that this triangle here is commutative, and the same thing on the other side. So if this is true, since phi tilde are isomorphism, then they are true also over for the GIs themselves. But this map, what is this map? This restriction here is just this map coming from u infinity bar to s. So this is just u infinity bar to x on both sides. So in other words, everything checks out, and I think I'll stop here because otherwise people will be upset with me. But okay, now we have proven step number 2. Step number 3, what was going to be was to take a projective curve, so something which is closed inside of a projective space, and show that its normalization is also closed. But now we said we at least have one very interesting ingredient. I take a projective curve, quasi-projective curve, let's say. Its normalization is quasi-projective. I can find a projective space where it lives inside. Okay. So hopefully this hasn't been too confusing, and I think we'll do a short course. We can do that maybe next week. A very short conference session next week, and then close with the closing remarks. All these things. Okay, yeah.